Okay, so we're going to begin the last portion of the cardiovascular physiology lecture. And where we left off was we were going to head into the mean QRS vector. Okay, so we just briefly talked about all of the vectors before and what they mean, that vectors show direction and magnitude. And then now we're going to go into the mean QRS vector. So if you add up all the small vectors that occur simultaneously during ventricular depolarization, we will come up with one large vector, and that's this vector right here. Okay, that's the mean QRS vector. So if we add up all of the small vectors that occurring simultaneously during the ventricles depolarizing, we will get this one major vector right here. Okay, this originates at the AV node. In a heart that is positioned anatomically correct, the apex of the heart is positioned down to the left and slightly anterior. Okay, so the heart is pointing down, slightly to the left, and slightly anterior. The mean QRS vector, which represents depolarization of the ventricles, would point in the same direction as the heart. That's why it's going down and to the left. To the left and inferiorly and anteriorly. If anything were to cause the myocardium to be displaced and change its anatomical position, the direction of that mean vector would also be altered. So being able to analyze the direction of that vector is why we designate this circle. Okay, so if we see right here, and we're talking about the mean QRS vector, again, as if we add up all those small vectors that are occurring simultaneously in the ventricles, we will come up with one large vector, and that is going to be represented here. So here we have that central terminal of Wilson, which will be considered the AV node. And this is that mean QRS vector, which if we were looking at the heart this way, this is pointing down and to the left, inferiorly, and then slightly anteriorly. So that's where the mean QRS vector is going to appear. Okay, so let's continue on with these three major vectors of the heart. So our first vector is the depolarization of the septum. This is the initial portion of that QRS complex and is triggered by the septofascicle of the left bundle branch firing. This vector points to the right and superiorly, so up and to the right. The second vector is the mean electrical vector. This is that major vector of ventricular depolarization. It's that QRS vector we just talked about. It points down and to the left. Sum of all small vectors representing ventricular depolarization. So this represents the middle portion of the QRS complex, and then it also represents the depolarization of the apex of the heart. So the third vector is the depolarization of the base of the heart, and this points to the left end superiorly, so up and to the left. Okay, so if we wanted to look at the three main vectors in this plane that we were just talking about, this would be 1, this would be 2, and this would be 3. So remember we talked about the first vector was that septum depolarizing, and it points to the right and superiorly. And then 2 is that mean QRS vector down here that points down and to the left. And then this is the base of the heart vector, which is pointing up and to the left. So the base of the heart, the septal firing, and then that mean QRS vector. And then remember that this is the AV node, or that central terminal of Wilson. Okay, so to finish up this presentation, we are going to give 3 summary statements about vectors in general. 1, when a vector that represents cardiac electrical activity points towards a positive portion of a lead, the deflection in that lead will be an upward or a positive deflection. 2, the maximum positive or maximum negative deflection occurs in a lead that is most parallel to the electrical vector. The greatest amount of deflection in a lead that is running parallel to the mean electrical vector. Again, to that QRS one we were talking about. 3, no net deflection occurs in a lead when the vector is moving perpendicular to that lead. Why? Because some of it is moving towards that vector and some of it's moving away. So it gives you a biphasic wave. So then you won't see a net deflection because we are moving some towards one way and then moving in an opposite direction. So you will not see, it will pretty much gives you what's called a biphasic wave, and you will not see a net deflection occur in a lead when that is occurring, when the vector is moving perpendicular to that lead.